Let's consider some one-sample hypotheses concerning the mean using the t-distribution. And when we do this, let's start off by structuring our null and alternate hypotheses. So here we have a one-sample test, one-sample hypotheses, which means we are just comparing one sample to some theoretical value. So in this case, we have the null hypothesis that mu is equal to c versus the alternate hypothesis that mu does not equal c. The example we'll use will be from some rats that have been forced to exercise on a treadmill. There are 10 rats, and they are put on this treadmill regime, and then following that we're going to record their weight change. So we weigh them initially, put them on the treadmill over a period of weeks, and then weigh them again. So our hypotheses are two-tailed, and what I mean by that is that the weight of the animal may increase or may decrease. We really don't know what's going to happen here. So we're going to reject the null hypothesis if there is a weight change, and we'll accept the null hypothesis if there is no weight change. So the weight changes that we record are plus 1.7 grams, 0.7, minus 0.4 grams, and so on. Our null hypothesis then is that mu is equal to 0. That's consistent with the idea that there is no weight change, so our theoretical value is 0 grams. The alternate hypothesis is that mu will not be equal to 0. We'll use an alpha of 0.05, meaning that we want to be right when we make a decision about the null hypothesis 95% of the time, but we're willing to be wrong 5% of the time. Our sample size is equal to 10. We compute the sample mean, and that's minus 0.4 grams. The standard deviation is 1.22 grams. And then the standard deviation of the mean, or the standard error, is equal to 0.39. We compute the t using the equation that we developed in the previous little video, and we determine that t is equal to, our computed value of t is equal to minus 1.026. Nu, which is our degrees of freedom, is n minus 1 is equal to 9, so 10 observations minus 1 is equal to 9. We lose 1 degree of freedom because we're estimating the parameter mu. And then our tabled value of t for an alpha value of 0.05 and a two-sided distribution with 9 degrees of freedom is 2.262. Notice that this value of 2.262 is more extreme than the absolute value of our computed value of 1.026. In other words, our 95% limits for the t-distribution are minus 2.262 and plus 2.262, and our computed value of 1.026 lies within those bounds, and for that reason we are not going to reject the null hypothesis. That is, there is no difference in, there is no weight change in these rats following this exercise regime on the treadmill. Some of the rats put on weight, probably as muscle mass, and some rats lost weight, but there was no consistent pattern. Now what we're going to do is shift gears a little bit and stay with a one-sample hypothesis, but this time it's going to be a two-tailed hypothesis. In the previous example, it was a two-tailed test because we had no a priori knowledge of whether the exercise should result in weight gain or weight loss. Now we've developed a drug perhaps, and we hypothesize that the drug is going to result in weight loss in humans. We get 12 human beings and we administer the drug to them, and then we record their weight change after a certain period of time. And the values are given here, 0.2 pounds, minus 0.5 pounds, and so on. Now, our null hypothesis is that mu is going to be greater than or equal to 0 versus the alternate, that is, mu is going to be less than 0. So the alternate hypothesis is consistent with our research hypothesis that this drug results in weight loss. Again, we'll use an alpha value of 0.05. N is equal to 12, so nu is going to be equal to 11. X bar, the average weight change, is minus 0.61 pounds. our standard deviation is 0.63 pounds, and standard error is equal to 0.18 pounds. Now our computed t is minus 3.389. Here you see nu, or our degrees of freedom, is equal to 11. Our tabled value is 1.796, so 95% of the observations should fall within minus 1.796 and plus 1.796. Our value, our computed value, is more extreme than those limits, and for that reason we reject the null hypothesis of no weight change. So this drug did result in weight change.